So on today's class, we are going to study Bessel function. Bessel's function. So this one is another special function. Another special function. Special function. All right. So as we know, we need a differential equation. So the differential equation for Bessel's function is the differential equation. The differential equation for Bessel function for Bessel's function is x square d square y upon dx square plus x dy by dx plus x square minus n square y, which is equals to 0. Alright, so the differential equation for Bessel function x square d square y upon x square plus x upon dy upon dx plus x square minus n square y is equals to 0, where n is some integer. So for that, say this is equation 1. We need the solution for this differential equation. We assume, say y is the solution for differential equation, this differential equation, which is something summation r tends to 0 to infinity ar x to the power k plus r be the solution. All right, be the solution. This solution is a kind of increasing solution. All right, the first term will be smaller than the another term will be greater than the first one. So we had taken the series in a increasing order. That's why I had used a k plus r. So if we have y equals to this much, so we want dy by dx, so dy by dx must be your, but dy by dx must be summation r tends to 0 to infinity ar k plus r x to the power k plus r minus 1. If you want another differentiation of this, so or we can say the double derivative of y, so this must be d square y upon dx square is equals to summation r tends to 0 to infinity, this is ar k plus r as it is, then this must be k plus r minus 1, this is your k. All right, this is k plus r minus 1 x to the power k plus r minus 2. So we have the value of y dy by dx and d2y by upon dx square. So we need to substitute this in equation 1. All right, so we have x square d double derivative of y is this much. How much? Summation r tends to 0 to infinity ar k plus r minus 1. All right, x to the power k plus r minus 2 as it is this. Then plus here is x, right, is as it is. Summation dy by dx is how much? Summation r tends to 0 to infinity ar k plus r x to the power k plus r minus 1. Right, now we want what y, so we have another term x square minus n square. Our y is summation r tends to 0 to infinity ar x to the power k plus r, which is equals to 0. So we had substituted this value in equation 1. So we have assumed our solution in an increasing order. So now we have to arrange all these terms into increasing order. Arrange these terms in increasing order. in increasing order. All right. So if we see here, if I multiply x square with this x, so this will give me x to the power k plus r. All right. And here we will get x to the power k plus r. All right. And if you will see here, if I multiply x square with this term, so this will give me x to the power k plus r plus 2 and minus of n square this much k to the power. So the smallest term we will have x to the power k plus r. We have only two terms. First one is k to the power, sorry, x to the power k plus r. Then another one is from here, from this. If I multiply x square to this quantity x to the power k plus r, so this will give me x to the power k plus r plus 2. So I know k plus r is smaller, so I need to write this term first. So we will get only two terms here. Just to summarize this, I know summation r tends to 0 to infinity ar is going to be constant. So I take this as common. So from here, if I multiply x square with this x, so this will give me x to the power k plus r. All right. Why? Because this is plus 2 and here minus 2. So this will give me only x to the power k plus r. So the coefficient is going k plus r, k plus r minus 1. If I see here, this will give me what? How much? If I multiply x to this x, so this will, here is power of x is 1. Here is minus 1. So this will give me x to the power k plus r only. So the coefficient is k plus r from this term. All right. So if I multiply x square with this, so this will, this is going to be what? X to the power k plus r plus 2. So I want only x to the power k plus r only. I want this. So if I multiply minus n with this term, so this is going to be what? This is going to be minus of n square with a multiply of x to the power k plus r. And we have only one term left. Which one? When x square is multiplying with this term. So this is summation r tends to 0 to infinity ar. If I multiply x square with this term, so this is going to be, this r must be on subscript, right? So this is coefficient. So how much x square multiplied by x, this will give me x to the power k plus r plus 2 is equals to 0. All right. Now I want to compare the coefficient. So coefficient of x to the power k. So I will get only when I put r equals to 0 in first term. Which is first term? This is my first. This is my second in first term. So the coefficient of this is 0. So the value is only here. The left quantity is x to the power only k. So we need to put r equals to 0 in first term. So this will give me how much? A0, A0. This will give me only k. This will give me k minus 1 plus of k minus n square is equals to 0. There is no any term. The coefficient is 0. That must be 0. So I can take k common. So this will give me how much? A0, k is common. So the left quantity must be k minus 1 plus 1 minus of n square equals to 0. This is cancel out. So we have a0 equals to k square minus n square equals to 0. So I can write this as a naught k plus n k minus n is equals to 0. I know a naught cannot be 0. So k take the value n minus n. So we have the value of k is n minus n. So we have coefficient of x to the power k. So the next term will be x to the power k plus 1. So we need to calculate what coefficient of x to the power k plus 1. If I look closely, so when I will get k to the power x to the power k plus 1, only when the value of r is 1 in first term. All right. So put the value of put r equals to 1 in first term. First term. So what is my first term here? So this is going to be what? Okay, let me write here the first term only. This is ar k plus r minus 1 plus k plus r minus n square. All right. So put the value of r equals to 1 in first term. So this is going to be what? A1 k plus 1. All right. Second k plus 1 minus 1 plus k plus 1 minus n square is equals to 0. A1 is equals to k plus 1 is common. Here we will get this is cancelled out. This is k plus 1 minus n square is equals to 0. So this is your what? A1 equals to k plus 1 whole square minus n square is equals to 0. So A1 can be k plus 1 plus n, k plus 1 minus n is equals to 0. So this is the final legend for the coefficient of what? X to the power k plus 1. So if you put the value of what? K equals to n minus n, we can see it is not 0. If you put the value of n plus 1, so this is not 0. It is not 0. So that means A1 must be 0. All right. Now I can calculate x to the power for the coefficient x to the power k plus 2, x to the power k plus 3, or in general I can calculate k to the power k plus r. All right. So coefficient of what? X to the power k plus r. So where I can find x to the power k plus r? I can see the first term is all ours what? How x to the power k plus r is already given. And I can see here if I substitute in second term what? R equals to r minus 2. So this will give me what? Already we have k plus r plus 2. We need to put the value of r equals to r minus 2. So the x becomes here r minus 2 plus 2. I can see this is going to be cancelled out. So the final version k plus r. So I can get k plus r from the second term when r equals to r minus 2. So the first term is as it is. First term is as it is. So this is going to be what? So the first term is our, we have from the first term, the coefficient of first term must be AR. This is k plus r minus 1 plus k plus r minus n square plus second term only r minus 2. So the coefficient left is only r minus 2. That must be equals to 0. If I simplify this, put r equals to r minus 2 in second term. Second term. This is nice. All right. And from the first term as it is. First term gives the original value, gives the original term. All right. So for the second term, we want coefficient x, x to the power k plus r. So this will only, we can get only when r is equals to r minus 2. All right. Now, just to simplify this is ar is equals to, take k plus r common. So we have left from here and here k plus r minus 1 plus 1 minus of n square plus ar minus 2 is equals to 0. Then we can see this is cancelled out. This is going to be the square of this one. So k plus r to the power 2 minus n square plus ar minus 2 is equals to 0. I know the formula of a square minus b square, a plus b, a minus b. So this is k plus r plus n, k plus r minus n plus a minus 2 is equals to 0. So this is in subscript, all right. Good. So if I need to calculate the value of ar from here, so ar must be negative of ar minus 2 whole upon how much? This term only. K plus r plus n, k plus r minus n. All right. Now put the value of what? For k is equals to n. For k equals to n, ar is minus of ar minus 2 whole upon the value of k equals to n plus r plus n plus r minus n. So this is cancel out. So ar is your minus of ar minus 2 whole upon how much left? This is r multiplied by 2n plus r. So this is a general item. Good. Now we need to calculate what r equals to 2. Because a0, a1 we had calculated, I need to calculate what? A2. Put r equals to 2. So a2 is your a0 whole upon 2 2n plus 2. Good. So this is the value of a2. Put a3. So a3 only when r is 3. So this is a3 is equals to 3 minus 1. This is a1 whole upon 3 2n plus 3. Good. But I know a1 is 0 already. a1 is 0. So a3 is 0. So I can say a1 equals to a3 equals to a5 equals to a7. All the terms are going to be 0. Alright. So now a4. a4 only when we will put r equals to 4. So a4 is your generalized term 4 minus 2 a2 minus of a2 upon r is 4 a2 n plus 4, and we know the value of a2. a2 is how much? Minus of a0 of 2 of this. So this is going to be how much? a0 minus minus plus 2 4 2n plus 2 2n plus 4. Good. So we can calculate further. So now we need to put this value in our generalized solution. So what we have assumed the solution, we have assumed what? How much? Y is equals to summation r 0 to infinity ar x to the power k plus r. But we have calculated what? For k equals to n. For k equals to n, we had y equals to summation r tends to 0 to infinity ar x to the power n plus r. If we expand this summation form, so y becomes here how much? For a0, this is a0, and this will give me x to the power only n. Then after a1, x to the power n plus 1. Then after a2, x to the power n plus 2. Then after a3, x to the power n plus 3. Then after a4, x to the power n plus 4, and so on. I know a1, a3, and a5 are going to be 0. So I just remove these. Why? Because I know a1 equals to a3 equals to a5 equals to a7. All these values are, so on, all these values are 0. So I just remove from here. So first term a0 x to the power n. For a2, I know a2 is how much? A2 minus of a0, 2 of plus 2n plus 2. So this is minus of a0 upon 2 dot 2n plus 2 x to the power n plus 2. Then after a30, a4 is a4 in terms of a0 is here plus positive of a0 of 2 4 2n plus 2 2n plus 4 x to the power n plus 4 minus so on. Alright, is a0 upon 2 4 x 2n plus 2 2n plus 4. Good. So this reason goes on. I can see a0 is common in all the terms, so I can take a0 as common. The left quantity is x to the power n minus of 1 upon 2 2n plus 2 x to the power n plus 2 plus 1 upon 2 4 2n plus 2 2n plus 4 x to the power n plus 4 minus so on. Alright, if we put how much? A naught equals to 1 upon 2 to the power n factorial, or sorry, gamma n plus 1, which can be written as, or we can write it as a naught 1 upon 2n factorial n. Alright, I can write factorial into gamma function form. So if you put, so the Bessel function is denoted as, y is known as Bessel function, y is known as Bessel function of first kind, and it is denoted by gnx. Alright, so gnx is equals to 1 upon 2 to the power n plus 1 x to the power n minus 1 upon 2 2n plus 2 x to the power n plus 2 plus of 1 upon 2 4 2n plus 2 2n plus 4 x to the power n plus 4 minus so on. Alright, I can multiply gamma n plus 1 inside 2 to the power n also. So just multiply this inside. So we will have gnx equals to 1 upon gamma n plus 1 x to the power x upon 2 to the power n power is n same, so we can write it as x upon 2 to the power n minus of 2 to the power n into 2 to the power n plus 2 gamma n plus 1 x to the power n plus 2. All right, plus 2 to the power n 2 multiplied by 4 2 to the power n plus 2 2 to the power n plus 4, sorry, 2n plus 4 2 2n plus 4 into gamma plus 1 where x to the power n plus 4 minus of then this is continue. So we have this. All right, so just write it at 1 upon n plus 1 x to the power 2 to the power n. All right, minus of, I can see if I take 2 common from these two factors, so this will give me 2 to the power 2 and 2 to the power n. So uh, on the combination of both these, this will give me 2 to the power n plus 2. All right, so we have summation multiply of 1 n plus 1 because 2 I had taken common gamma n plus 1 x upon 2 to the power n plus 2. All right, 2 to the power n is here to the, 1 power n, so n plus 1, and we had taken common 2 from this factor, so this will give me 2 to the power n plus 2. So I'll written this here plus same here 2 to the power n, and we have just multiplied it, but I had take common 2 from here and 2 from here, so this will give me how much, 2 to the power 2 and 2 to the power 2 is here, this 4 can be written as 2 to the power 4. So we have 1 multiplied 2, this as it is, this is 2 to the power 2 and 1 2 common here and 1 2 common, so this will give me 2 to the power 4. So collectively it is called 2 to the power n plus 4 in the left quantities, and we have n plus 1 n plus 2 gamma of n plus 1, and this will give me x upon 2 to the power n plus 4 minus so on. Now I can write it as gamma n plus 1 x upon 2 to the power n minus of 1 factorial. 1 can be written as 1 factorial. This can be written as how much? N plus 2 gamma n plus 2. Why? This we know what gamma n equals to n minus 1 into n minus 1. All right, so if I put here how much, n minus 2, sorry, n plus 2, if I substitute n, the value of n plus is n plus 2, so this will give me n plus 2 minus 1 gamma of n plus 2 minus 1, so this will give me n plus 1 n plus 1. So I had written what n plus 1 n plus and gamma n plus 1 is n gamma n plus 2 gamma n plus 2. So from this formula I had written. All right, so I can write this as n gamma n plus 2 x upon 2 to the power n plus 2. All right, plus 1 into 2 can be written as factorial 2, because if I open factorial 2 I can write 2 into 1, so this is same factorial 2, n plus 1 n plus 2 n plus gamma n plus 1 can be written as factorial n plus 3 n plus 3, and this is x to the power 2 to the power n plus 1. You can derive this from here, this formula. All right, so if you want to sum up these, so gnx can be written as summation r tends to 0 to infinity. First term is positive, then after negative, then after positive. So alternatively, we will have 1 minus 1 to the power r. All right. First is factorial 0, factorial 1, factorial 2, factorial 3. So I can write as factorial r. All right. Now we have n plus 1, n plus 2, n plus 3. So I can write it as n plus 1 or factorial gamma n plus 1, or I can add n plus 1 factorial. All right. Either I can write it as gamma because I know n equals to formula n equals to gamma n plus 1. Good. So I can write it this as, because this is going to be n plus 1 term. So I can write it as this. Then after, let me erase this. Now the left quantity is x to the power 2 to the power n plus 2r, because first term is n, then after 2, then after 4. So this is going to be n plus 2r. So we can say our gnx is, final gnx is, we can say the final gnx is, gnx can be written as summation r tends to 0 to infinity minus 1 upon r factorial r n plus 1 factorial x upon 2 to the power n plus 2r. So this is our Bessel function. Alright, Bessel polynomial. Or we can calculate simultaneously k equals to for minus n. So when we have the both the value, so I am not calculating individually. I can write it as simple k minus nx. It is going to be summation r tends to n to infinity minus 1 to the power r upon factorial r minus n plus r x to the power 2 to the power minus n plus 2r. This is going to be the value for k equals to minus n. So collectively or together the value of y will be a gnx plus b j minus n. So this is the exact value, the solution for y for the differential equation for Bessel's function. Thank you.